So we're still in Chapter 6, Solving and Graphing Inequalities. We're still in 6.3, Solving Compound Inequalities. Our targets, we're going to write, solve, and graph compound inequalities. And today specifically, we're going to model real-life situations using compound inequalities. So as we said the past couple days, compound inequalities are things that consist of two inequalities connected by the word and the word or. So those are the two things that connect it, two inequalities that make a compound inequality. We have a few special cases that we need to go over. So if I graph x is less than 5, so I'm going to put an open dot at 5. And if I want to graph x is less than 5, I'm going to shade everything to the left. So that's x is less than 5. Then if I graph x is greater than 6, so I'm going to put an open dot at 6, and I'm going to shade everything to the right of 6. So if we notice, this is an and statement. And with and statements, it's supposed to satisfy both of my inequalities at the same time. Since there is a gap right here in the middle, in my inequality for an and statement, we would say there is no real numbers that would make our solution true. Special case number 2. So we'll just call this special case number 2. Again, I have two different inequalities joined by an or statement. So my compound inequality is x is greater than 5 or x is less than 6. So if I graph my first inequality right here, I'm going to say x is greater than 5. So I'm going to put an open dot at 5. And I'm going to shade everything to the right. So we have x is greater than 5. On the left-hand side, I have x is less than 6. So I'm going to put an open dot at 6. And again, since it's less than 6, I'm going to shade everything to the left. If you notice here, now our inequalities goes like this. I'll make that a little better. Okay? So since our inequalities overlap, we would say our solution is all real numbers. So anything I would plug in here for x would make our or compound inequality true. Okay, so we have special case number 3 now. Here again, I have the compound inequality x is greater than 5 or x is less than 5. So I'm going to put an open dot at 5 right there, and I'm going to shade everything to the left. And that's not right, so hang on a second. I should have shaded everything to the right because x is greater than 5, so I'm going to shade greater than. Okay, then the other side of my inequality. I'm going to take a look at it. X is less than 5. So again, I end up putting my open dot at the same spot. So I have x is less than 5. So I'm going to shade everything to the left here. And I'm going to have x is less than 5. Now notice, my number line is highlighted everywhere except for the number 5. Number 5, it's not highlighted. So I'm going to say my solution is, I'm going to say x is, and I'm going to use the term not equal to. So x is not equal to 5. So what we're saying there, any other number works except for 5. So here's our first inequality application problem. We have the prices of fine art. In 1958, the painting Still Life with Apples by Paul Cézanne sold at an auction for $252,000. The painting was auctioned again in 1983 and sold for $28.6 million. So what we want to do is we want to write a compound inequality that represents the different values the painting was worth between 1958 and 1983. So we start with our smallest amount. We start with our 252,000, and I'm just going to write that down. I'm going to say 252,000. Now, the big decision, is this going to be an and or is it going to be an or? And what tells us is right here, this keyword between. Between translates to an and statement because I want my value to be somewhere in between my starting number of 252,000 and my ending number of 28.6 million. So on the right-hand side, I'm going to write 28.6 million. So I'm going to take that number here, and I'm going to write 28,600,000. Remember, this is an and statement. So in between here, I'm going to put less than X and less than X. The next thing I have to consider, do I want to consider and include the numbers 252,000 and 28.6 million? Are those included in the price? And since the painting was sold for 252,000, I do want to include that number. So I'm going to put equal to on both of those as well, because I do want to include both numbers. So our next compound inequality, we have a friend, Bill, who lives 3 miles from the same school as another friend, Mary, who lives 2 miles from the school. So you wish to estimate the distance D that separates their home. So the first question, A, what is the smallest distance D we might have? Well, you can see we have a picture of it over here. We're going to say that the school is in the middle. We're going to say Bill's house is this dot up top here, the red dot. And we're going to say Mary's house is right here. So now that we have our picture set up, to start out with, it says Bill lives 3 miles from the school. So if I just drew a line straight to Bill's house, that would be 3 miles. Okay? And then it says Mary lives 2 miles from the school. So if I drew a line to Mary's house, that would be 2 miles. Okay. So what's the shortest distance or the smallest distance we might have? Well, to figure that out, what we're going to do is we're going to take and move Bill's house so it lines up with the school and Mary's house. So now if I take a look at that, I know that my distance from here to here was 3 miles, right? So if I take away the distance from Mary's house to Bill's house right here, we're only going to have 1 mile left. So the shortest distance, or the smallest distance from Mary's house to Bill's house is going to be 1 mile. So to figure out what is the largest distance we might have, I'm going to erase some of this and kind of make my picture over again a little bit. So again, we have Bill's house right here on the outside. We have Mary's house right here, and we have our school right here again. And the longest distance that Bill's house could be away from Mary's, if I take and rotate this around a little bit more and put it on the opposite side of the school as Mary's house, now I have the longest distance. Okay, so again, we want to figure out the longest distance from Mary's house to Bill's house. So to do that, I I have to cover the 2 miles here back to the school. And then I have to cover the 3 miles to Bill's house. So that's going to give me a total of 5 miles. So now I have part A answered. What is the smallest distance we might have? Then I have part B answered. What is the largest distance we might have? Now I want to write an inequality that describes all the possible values that D might have. Okay. So if I write that, I'm going to start out with my smallest distance of 1 mile, and then my largest distance, which was 5 miles. And since I want all the values in between there, this is going to become an AND statement, so my X is in the middle. Now the question is, do I want to include 1 mile and 5 miles? The answer is yes, those are included in there. So I'm going to say less than or equal to, and less than or equal to here. So my final answer is 1 is less than or equal to X, which is less than or equal to 5.